So, hello everybody, thank you for being here. I present you Alexia.
I present Pauli.
And I present Flo. We're three physicists. We work at different institutions, but we work in the same field. And today, despite the quantitative nature of our field, which is quantum information theory, we'd like to present you some fundamental aspects of our field in a qualitative way.
So, let us start by presenting you Sir Isaac Newton. This physicist is most famous for having taken an apple in his face, but for us physicists, he is really important because he developed classical physics. Okay? Classical physics is a theory that says that if you know all the parameters, like the strength of the wind, the size of this ball, the weight of this ball, you can predict everything that is going to happen, the whole trajectory and where it's going to end. So, for example, a good basketball player would be able to pass this classical ball exactly through the second wall you can see. So the fact that knowing everything allows you to predict everything is called determinism.
And so in this case, if Isaac Newton had known everything about the apple that was in the tree above him, then he could have predicted that it would fall on his head and maybe he wouldn't have had a concussion. But in quantum physics, things are different. So if you take the same scenario, so you use instead a quantum ball, so that means that you are going to consider like the whole system here as something that is much smaller, because that's the scale at which quantum physics is valid. So for instance, the quantum ball can be a particle. Well then, even if you know everything about this quantum ball, you cannot predict everything that's going to happen to it. So it could go through the hole above with some probability, and through the other hole with another probability. So in quantum physics, even if you know everything, you cannot predict everything. So you don't have a deterministic explanation of nature, but a probabilistic one.
Yes, but if we tell stories or anecdotes about physicists, let's also tell one about Niels Bohr here, we see in the picture. One of the pioneers of quantum mechanics, and once visited by some of his colleagues in his holiday house, they noticed a horseshoe above the entrance, and they asked him, "Oh, but Niels, why do you have a horseshoe above your entrance? Do you believe in this bullshit?" And Niels answered, "The people who gave it to me, they said it works even if you don't believe in it." And so a lot of people in this time, or a lot of people were happy with the new theory, some weren't. And one of the pioneers that wasn't happy with the new theory was Albert Einstein. And in 1935, he came up with a Gedankenexperiment that should prove that quantum theory is not complete. And this proof works by contradiction.
And so his plan was that quantum mechanics should actually be completed. But you might be wondering, what do we mean by complete theory? How could we complete such a theory as quantum mechanics? So imagine that you have an event E in space-time, so time goes that way. And this event E, you don't know if it's going to happen for sure or not, but you have some probability with which it can happen, some probability P of E. And now suppose that in the past of E, which is represented by this cone here, there are some lambdas that are actually hidden variables. And what Einstein said is that maybe there exist such lambdas, and if we knew everything about them, then we could predict if E is going to happen or not in a deterministic way. So how can variables or parameters be hidden? Well, they can be like too difficult to access. It can be like beyond our technological power to access them. So one simple example is that perhaps they are too small, and this has happened in the past. For example, before we had microscopy, we didn't know about atoms and things like that. So a possibility that could be is that there are some variables, some parameters that are too small to access, and if we knew about them, then we could have a theory of quantum mechanics that is completely deterministic, and we could thus complete it.
So you maybe wonder what these hidden variables are. So for example, if I were to prepare like 200 envelopes, and I would put in each of these envelopes a red card or a blue card, and I would send it to you, you would open the envelope and see, well, either a red card or blue card, but for you it would happen to be completely random. But the explanation behind it would be me choosing a red card or blue card in this specific envelope, and you seeing this envelope having a red card and the other one being blue. So in this case, I'm the hidden variable behind this. I'm the explanation for this.
So we're still in the 30s historically, and you know, like after Einstein and Podolsky and Rosen came up with this Gedankenexperiment and the paradoxon that follows, a lot of things happened in the next decades. For example, we had a period of industrialized terror and fascism, and also, like, thanks here to Barcelona for the resistance, not all people follow this. And in physics, it was the time of the shut up and calculated interpretation of quantum mechanics, so to say. But there were some people that did not stop thinking about it, and one of them was John Bell, and he basically managed in the 60s to put this Gedankenexperiment into mathematical equations. So what did he do? He assumed that every theory, there's basically two assumptions it can fulfill, like a physical theory. For example, that nothing can go faster than light would be the first assumption, and the second, that there exists a local hidden variable that can explain you things deterministically. And because of he managed to also well define these assumptions mathematically, he was able to derive a set of inequalities, which we nowadays call Bell inequalities, which every theory that fulfills these two conditions has to satisfy. And so to recap, so every local hidden variable theory satisfies Bell inequalities, and this in turn means that a deterministic explanation of the world is possible.
But now if we take the reverse, so we use quantum mechanics, we put the math inside these inequalities, and we see that these Bell's inequalities are actually violated. So what does that mean? It means that one of the two assumptions we made, so that nothing goes faster than light or that local hidden variables exist, cannot be true. So since the first one is that stuff can go faster than light, and this is highly improbable, and that would screw with the theories of relativity of Einstein, what this is accepted to imply is that local hidden variable theories are not explaining what we are seeing. This, in turn, implies that determinism is not possible in these experiments, and if there is no determinism, it implies randomness, true randomness.
But one thing to pay attention to here is that even if theoretically quantum mechanics violate Bell's inequalities, it doesn't mean that nature does so. Maybe nature satisfies Bell's inequalities and we simply need another theory to describe nature. So to know that, physicists had to wait for experiments to be done. And this is about 20 years later with this beautiful guy, Alain Aspect, who used two separated labs. That's like the basic scenario for such an experiment. And he used systems of photons. And he managed to observe an experimental violation of Bell's inequalities. So this means that the world can truly not be described by a local hidden variable theory. And this is what we call non-locality. And as Florian Pauli explained, this means that, since there is a relation between non-locality and randomness, this means that there is truly randomness in the universe.
But now we have a problem. So we know that randomness exists. But now I come to you and I give you some numbers and I tell you these numbers are random. You can trust me and take them as random, but you would like to certify this. You cannot prove these are random. So to illustrate this small problem, we have a little comics we let you read. You have to be fast in reading. Okay. So in this situation, you see that I give you a string of numbers, and what you would like to do is mathematically prove that these numbers are really random, to be sure about it. So usually we do that by imagining that there is a super spy, illustrated by this magnificent robot, and this super spy is a quasi-god, meaning that he knows everything about the world. He has every parameter. So he knows everything, and what he's going to do is try to predict your numbers. So if he manages to do this, it means that your numbers are not truly random, since someone can predict them. Okay? But now what we can do is make a setup, make an experiment in which we have the mathematics and we can come to the proof that these numbers are really random. The mathematics exist, and this is actually our job. Come with this mathematics and prove it.
Okay, but wait, like if I translate this binary number into decimal, it gives me 99999.
Yes, true. So actually this string here is a 9999 in base 10, but what we can do in our field, this is our work, we use trivial mathematics, as you can see. And okay, don't worry, you don't have to understand this slide. We just wanted to look a little nerdy for a while. And so Well, the takeaway message is that there exists mathematics such that we can prove what we said before. The numbers we get as outcome of the experiments are really random.
So what we have told you today has implications on two levels. First on the practical, but also on the philosophical level. So practically, there is a big demand for random numbers. Scientifically, for instance, potentially for a quantum computer, and also simply for simulations. And there is also a demand for random numbers in a more commercial area, for instance, for private communications in cryptography, casinos, etc. And philosophically?
Yes, and we also have really nice philosophical implications because first we're able to put our worldviews into test in the lab, or like not the worldview itself, but maybe certain combinations of worldviews and say whether the combination can exist or not. And as theoreticians, it's also a nice playground to play around with things where we still have no physical evidence of, but treat them as possibilities we have to research.
And to end our talk, we wanted to talk to you about the limitations of our subject. So these limitations, they reside mainly in the loopholes that can happen in the experiments. So it will be problems in the experiments that you can only fix if you make some assumptions at the beginning. And so the first two loopholes, we think that they are going to be solved soon by scientists. But the third one is a bit more tricky. It's the free choice loophole, because you have to assume that at the beginning of your experiment, there is already a small amount of randomness if you want to guarantee more. So this means that you have to assume that there is free choice in the universe. So it's a bit philosophical, and it also makes the whole thing a bit circular.
Yes, thank you for your attention, and thank the organizers for this nice conference.